All right, so A asks us to find the limit as x approaches infinity of g of x. So what I would do for this, you're doing the limit as x approaches infinity. These negative exponents, I would move them to the bottom so they are not negative anymore. So x over e to the x plus b over e to the x here. So as x approaches infinity, this is like a Bobo-Botno situation. So we've got x over e to the x. What is that going to approach as our numbers get really, really big? That'll be 0 because that one's bigger on the bottom. E to the x is bigger than x to any power. So that is going to approach 0. What about b over e to the x? Also 0. You don't have to write that middle step there if you don't want. So that's just going to give you a limit of 0 for that. We're okay there. For b, it says for what positive value of b does g have an absolute maximum at x equals 2/3? Justify your answer. So for looking for absolute maximums or minimums, we need to look at the derivative and find critical points. So I would probably do it this way. I would take g of x and I would factor out this e to the negative x. I don't know if I did it that way on the solutions. Who knows what I was doing on these particular solutions. Did I do that here? I think I took the derivative first, then factored it out. You can do it either. Let's do it this way, just so you can see one more option. So if you use this, you got to use product rule. If you do it like it is from the beginning, you'd also have to use product rule for that. You'll just use product rule twice. So g prime of x would be e to the negative x times, you got the derivative of x plus b. Derivative of x is just 1. The derivative of b, because b is a constant, is 0. I'm going to write it just so you guys are with me, but you don't have to write it. Then we would have x plus b times the derivative of e to the negative x. The derivative of e to the x is e to the negative x, but you got to use a chain rule there, which is going to give you a negative right there. So you end up there, that's just e to the negative x. Let's distribute here. So, okay. So if we distribute this here, we're going to get minus e to the negative x times x minus e to the negative x times b. And all of those terms have an e to the negative x, so it's going to be to your advantage to factor that out. And when you do, you get 1 minus x minus b. And so for this, you are looking, when you're looking for maximum minimums, you're looking for where the derivative equals 0, because that's where it may switch from positive to negative. So if we set this equal to 0, you would have e to the negative x equals 0 and 1 minus x minus b equals 0. E to the negative x never equals 0. So that doesn't give you anything right there. If you try to solve it, you end up doing like a natural log of 0, and you can't do natural log of 0. So over here on this other side, we have 1 minus x minus b. So if we solve that for the x right there, we could just move the x over to the other side. So we'd have 1 minus b equals our x. That. And let's see. We want the maximum to be at 2/3. So we want this 1 minus b to give us 2/3. We want that maximum to be there at 2/3. I think. This is right. Let me peek at mine. Yeah. Okay. That's what I did. All right. So we want this value. We want x to equal 2/3 there. So we want 1 minus b to equal 2/3. And so if you subtract 1, negative b equals negative 1/3, and b equals positive 1/3. So that tells us like that would give us the critical point at 2/3, but we have to justify that it would be a maximum. So if I say if b equals 1/3, then we know g prime of x would be e to the negative x times 1 minus x minus 1/3. And so if we make a sign line for that, our g prime of x would have a critical point at 2/3, and the e to the negative x and the 1 minus x minus 1/3. You really could make that 2/3 minus x there. E to the negative x is always positive, so it doesn't really affect your derivative there, the sign of your derivative. So if we plug in a number like 0, we're going to get 1 minus 1/3, which is going to give us a positive number right there. If we plug in a bigger number like 1, we would get 1 minus 1 minus 1/3. We'd get a negative over here. So you get a positive and a negative. So what's happening here, because this is the only critical point you would have for this graph, which means this graph of g of x would be increasing and then decreasing. So that has to be the absolute maximum, because if you only increase up to that point and then you only decrease after that point, there are no other possibilities for a maximum or minimum. So we would say since g prime of x is greater than 0 for x less than 2/3, g increases on that interval, and since g prime of x is less than 0 for x is greater than 2/3, g decreases on that interval, therefore g has an absolute maximum at x equals 2/3 when b equals 1/3. There. Switching from positive to negative only guarantees a relative maximum. So I think you would be okay to say that there is a relative maximum at x equals 2/3 because g prime switches from positive to negative, and that is the only critical point on the graph. like, so you would need to go a little bit further and say, since this is our only maximum or minimum point, it has to be the absolute. Because if there was a possibility for others, then it wouldn't necessarily be absolute for that. So in some fashion, you have to go a little further than just the switches from positive to negative, because that only guarantees a relative maximum minimum. It could be. I wrote 1 minus x minus 1/3, but if you combine those like terms, then it would be negative x plus 2/3. So that would be the same, and it doesn't matter which way you write that. Mm-hmm.
The 1 minus x equals 1/3, and like solve for x and show that x equals 2/3. Do we need to do this?
I don't think so. Yeah, I don't think. I think that this right here could be left out because we found that value. So, and I kind of like rewrote the function here, which you can do if you would like, but you need this like if b equals 1/3, and then you need to show doing that sign line for g. You definitely don't have to write this like equation for g. I would probably write the equation for g prime, which I put my e in the bottom on here and did not when I just did it now. But this over here I think would be optional for that. I don't think you would have to do that. And I also, whenever I just worked it out now, I made like the chart right here where I did not do that over here. It's fine either way, but make sure that you label it g prime of x. So you can use the chart if you would like, but you don't have to. Okay. Then for our last part, find all values of b, if any, for which the graph of g has a point of inflection on the interval from 0 to infinity. Justify your answer. So if we're worried about point of inflection, what are we going to have to do? Second derivative. So g prime of x, let's see how I did that here. Did I make it? Okay, I used quotient rule because I wrote it like this. Whenever you have e to the negative x times 1 minus x minus b, like that, it can be written 1 minus x minus b over e to the x if you want to write it that way. So you got a couple options. You can use product rule with that negative exponent, or you can use quotient rule. I think I used quotient rule. So if I use quotient rule, it'd be e to the x times, this is just going to be a negative 1 when we take that derivative, minus 1 minus x minus b times the derivative of e to the x, which is e to the x, all over e to the x squared. So you can factor in e to the x out of the top. It's going to leave you with a negative 1 minus 1 plus x plus b. I'm just distributing that negative right there to that over e to the 2x. And one of those e to the x's can cancel, and you will get negative 2 plus x plus b over e to the x for your second derivative. And let me make sure that's right. X plus b minus 2 over e to the x. Yeah, that's the same. So if we're looking for a point of inflection, we're looking for where this would equal 0. So negative 2 plus x plus b would have to equal 0. E to the x could equal 0, but it never does, so that doesn't really give you anything there. So x would have to equal 2 minus b if you move the 2 and the b over. And then, okay, sign line here. What's it end up with? Okay. So, if we do a sign line for this, we got 2 minus b. We do know b is a positive number. So what we don't know is we do not know what b is, but we do know b is a positive number. So if we're trying to figure out whether this function is going to be positive or negative, we could plug in some different stuff. So let me, just for consistency, let me see what I did over here. Okay, that's what I was going to do. Okay, good. All right, so for example, if I know b is positive, I know 2 has to be bigger than 2 minus b. Because if b is a positive number, you're doing 2 minus some positive number, which is going to give you something less than 2. So if I plug in 2 over here, then negative 2 plus 2 plus b over e to the x would just give me b over e to the x. We know b is a positive number. We also know e to the x is going to be positive, so we would get a positive in that section. And then something less than 2 minus b. Since b is positive, like if we were subtracting that positive number, what I used here was like 2 minus 2b, because if we are subtracting a positive number, if we double the amount that we're subtracting, it's going to make it more, it's going to make it less than 2 minus b. So if I do that, I've got negative 2 plus 2 minus 2b plus b over e to the x. Sorry, I'm running out of room here. Go down here. So negative 2, positive 2, those will cancel. I'm going to have negative 2b plus b over e to the x, which is going to give me negative b over e to the x. Since I know b is a positive number, negative b would be a negative number. So we get a negative right here. So find all values of b, if any, for which the graph has a point of inflection at 0 to infinity. So this basically guarantees that it has to happen there, because it doesn't even matter what the b is. This is what should happen. But we do want to know that this falls on the interval from 0 to infinity. So 2 minus b has to be greater than 0. Because if 2 minus b is less than 0, then it's not on that interval there. So if 2 minus b is greater than 0, which would mean that negative b is greater than negative 2, which would mean b is less than 2, then 2 minus b is on the interval 0 less than x less than infinity, and g of x must have a point of inflection at x equals 2 minus b because G double prime of X changes sign. At X equals 2 minus B. So then B cannot be any bigger than 2 because it's going to cause that value 2 minus B to be negative for that. So this B is less than 2 minus B.
Do you not have to state like an interval that B has to be on, like from 0 to 2?
We probably should. They tell us B is positive. So you might could get away with this because we're saying B is less than 2, but the constraints of the problem also tell us B has to be positive, so it can't be any less than 0. So you might could get away with it as I have done it here. But it would probably be better to include, like I did on there, 0, B is between 0 and 2. Because since B is positive, it can't be any lower than 0 there. Yeah, yes. It is basically the same thing because we know that G is going to have, I went ahead and said that we know G is going to have a point of inflection at 2 minus B here because G prime changes signs. So I did the same thing here where I found that B has to be less than 2. So the point of inflection is only interval from 0 to infinity when B is between 0 and 2. I probably like my explanation on this one a little bit better than what I've done in class, but give you a little bit. Sometimes I like for you guys to see like a little bit different thought process. So the main points you have to state there is like for the point of inflection to fall on that positive interval, B has to be between, it's probably better to say between 0 and 2. Might get away with less than 2, but better to say between 0 and 2. And then you know that because G prime is going to have a point of inflection, or G is going to have a point of inflection because G double prime changes signs there. Okay, questions? I think these are difficult whenever this. I think just 2. Is that one example? Yeah, just 2. Just 2 examples. Because you already know how to do the basic process. The only thing different we're going to throw in there today is they're going to be definite intervals instead of just being the general indefinite intervals. So no plus C's on these. And so I'll let you write this down and I'll explain what we're looking at here. Yes, unless it is a differential equation problem, which we have not done yet, and then it might be 3 or 4 points off. Because you can't do the next steps of the problem if you don't have the plus C. So the plus C is really important. When we do differential equations, you will see why it's so important a little bit more. That'll be in Unit 7.
Is there a unit that like has like the worst testing? Have you already passed it yet?
It's probably tied between 4, which we've already done, and 8.
4 and 8.
Yeah. So 8. Yeah. So we are almost done with 6. 7 is pretty short. I think we'll be able to do it in a couple weeks, and then we'll have 8 to finish up. So my goal is to be done with new content early April. We'll see if we make it or not. And then that'll give us about a month to review, which is what I would like to have. because there's so much content going back over and remembering when to do what for, because on the exam it's all thrown together. It's not like here is integration, here is related rates. Like they don't. Yeah. They really like to give you, like for example, position problems, they really like to give you velocity as the equation. So then they're going to ask you something about acceleration, so you have to take the derivative. And then they're going to ask you something about the position, so you have to integrate. So you end up doing like everything in one problem. Yeah. Yeah, so yeah, they're pretty cool because it like ties all that we've learned together and sort of shows you how it works together. But yeah.
We're not doing it for nothing.
Yeah. Probably. Well, we might not get it in. Well, let's see when is.
You've counted it, haven't you?
Maybe. We really need to. I'm gonna try real hard to get that. Yeah. Because it's. We'll see. Because I hate having all of spring break. Of course, you're going to be gone, so it's going. Even though you're probably going to miss part of differential equations, which is not the worst thing to miss. It will be better than missing Unit 8. Right. You'll have a little time to make it, yeah. Yeah. It's just going to depend. We may end up having to take it after spring break. I don't like having a whole week off and then come back. And we won't do a Monday after spring break. I'll promise that at least. Okay, so our integral here, this is UDU substitution. So in this case, U would be your G of X, and DU would be the G prime of X dx. So the difference here is what we are going to do with definite integrals. We did do one of these problems the other day on that FRQ that we were looking at. We are also going to adjust our limits of integration. And what that's going to do is going to make it to where we don't have to go back to x's. So let's look at how this is going to work for this problem. And I tried to pick ones that were a little bit more difficult. Well, actually, this one's not that bad. Maybe it was the next one. But so we could see what was happening here. So u is going to be x squared plus 1. That would make du be 2x dx. So we've got this x right here that when we combine it with this dx, we can just put a 2 right here on the inside, a 1/2 on the outside. So when we substitute, this right here is my u, and then this stuff right here together, that's my du. So what I will have is 1/2 integral of u to the 3rd power du. Now, you have a couple options on dealing with your limits of integration. Okay? It is possible for you to do it this way where you leave this 0 and 1, but if you do that, you would need to say x equals 0 and x equals 1. And you would not plug that stuff in until you change everything back to x's. Or we can adjust this, and this is the way that I prefer and would suggest that you try. Since I know that x equals 0, I could do this. I could say if x equals 0, then u equals 0 squared plus 1, so u equals 1. So I'm going to put that right here and make my lower limit 1. So I have adjusted it from a x equals limit to a u limit. And if you do that, you do not have to put u equals 1 because this is a du integral, so it would be assumed that that limit matches the integral there. And then so we can do that same thing for if x equals 1, then u would equal 1 squared plus 1, which would give you u equals 2. And we would put that up here as our top limit of integration. So basically all we are doing is we're taking our limit, we're plugging it into our u. So u equals 0 squared plus 1, and then we're using that as our new lower limit. And then we're taking our top limit, we're plugging it into our u equation and using that as our top limit. The really good thing about this is if you do this, those are u values, which means you don't have to plug the x stuff back in at all. So what we are going to do for this is we're going to integrate. So we'll have u to the 4th power. That'll give us a 1/4 right here. And we will integrate from 1 to 2. You don't need the plus c since it is a definite integral. So we're getting, I'm just going to pull this 1/8 out here. And then we'll have 2 to the 4th minus 1 to the 4th. So 1/8 of 16 minus 1 is going to give us 15 over 8. Yes. Yeah, it'll work with every definite integral. And it's the preferred way to do the problem because it cuts out some extra steps. You could write it this way where you've got the x equals, integrate like we've been doing, plug the x back in, and then you would do the definite integral with that x equals value. But it's going to have more steps, which means more room for error. Also, sometimes these problems are not going to actually ask for the answer. They're going to ask for the setup. So it's going to tell you like u equals x squared plus 1, and it's going to give you options for your substituted integral. And if they do that, they almost always have changed the limits on it. So, okay, questions? If it is an indefinite integral, one that has the plus c on the end, you always have to go back to the x's. But for definite integrals, if you adjust your limits by plugging them into your u equation, you don't have to go back to the x's on that. We okay here? All right, let's do one more. Okay, this is one that's going to be that little bit more difficult problem because I'm sorry. I wasn't talking to you. Hunter's texting me. My husband is at home. But he's not asking anything. Oh. He also sent me a picture of a pair of ridiculous looking sunglasses that he wears. Yeah, he's not feeling good enough to do his schoolwork he's missing, but he's okay for online shopping. Okay, so u for this one is going to be 2x minus 1. Du is going to be 2 dx. So this is more like what you had yesterday because this is going to be your u. We can very easily make this right here our du just by adding that 2 here and the 1/2 out front. But like we were seeing yesterday, we've got that x right there that is still there and we can't replace it. So we're going to have to go over here to the side. U equals 2x minus 1. We are going to add the 1. U plus 1 is 2x. We're going to divide by 2. So I'm going to write it this way, 1/2 u plus 1/2. is our x. And so we're going to have to replace that x with this here. So, to substitute, we're going to have 1/2 u plus 1/2 over, I'm going to write this as u to the 1/2 power, du. So all of that part is the same as what you were doing yesterday. The only difference is we are going to take our limits and we're going to plug them into our u. So if x equals 1, then u equals 2 times 1 minus 1, which actually just still equals 1. Right? So our lower limit stays 1. Our upper limit, right here, if we plug that in, if x equals 5, u equals 2 times 5 minus 1, so we get 9. That's going to go up here, so we get 9 right there. And so since we have adjusted our limits, we never have to go back to x's on this problem. Everything can be done with u's. We got this u to the 1/2 here in the bottom. So we either got to like think love connection, or we got to think moving this up to the top, or we got like a u to the negative 1/2 times 1/2 u plus 1/2, and then distributing there. So we got 1/2 u to the positive 1/2 plus 1/2 u to the negative 1/2. So we must integrate. This is going to be u to the 3/2, and then we're going to find ourselves doing 1/2 divided by 3/2 out front. Do it in your head if you can, but if you can't, that's okay too. Write it out. Here we're going to u to the positive 1/2. We'll have 1/2 divided by 1/2 here. That you probably can do in your head. There is no plus c on this one because it's a definite integral. Instead, we're going to put this bracket on the end where we got from 1 to 9. And then 1/2 times 2/3 is just going to give you 1/3 right there. So we got 1/3. I'm going to also write it this way. Square root of u to the 3rd power plus the square root of u from 1 to 9. The way that my mind works, I can plug numbers into roots easier than I can fractional exponents. So I like to switch them back, but you don't necessarily have to. I'm going to stop for a second. Any questions so far? Yes.
So if there's changes,
Yes, yes. So when you integrate here, putting that bracket on the end to show the numbers that you're going to plug in whenever you actually evaluate it takes place of the integral. Yeah. So whenever you integrate, that's not needed anymore because you have integrated, but you got to put this bracket on the end. Okay, so if we plug in, we have 1/3. So we need lots of parentheses here. We got square root of 9 to the 3rd plus square root of 9. And then we're going to have minus 1/3 square root of 1 to the 3rd plus square root of 1. Now, Square root of 9 to the third is getting to be one of those numbers like if we do 9 to the third power, it's going to be like 81 times 9, and it's going to be a big number, and we might not know the square root of it. But square root of 9 to the third power is the same thing as the square root of 9 raised to the third power. What is the square root of 9? 3. 3 to the third is 27. So you'll see this stuff a lot of times on calculator inactive problems. And then this is a little bit simpler because it's just 1, so you don't even have to think. 1 roots of 1s are always going to be 1. So we got 9 plus 3 minus 2/3, no, 4/3. So 1/2, 12 minus 4/3. And that's going to be 36. So we're getting half of, let's see, 36 over 3 minus 4 over 3 is going to give us 32 over 3. And then I would reduce before I multiply, so this will be a 1, this will be a 16, and we should get 16 over 3. Now, on your homework, I want you to go ahead and get all the way down to a single number. You're going to need it to check your answer in the book, or if it has a pi or something, you may not be a single number. But on FRQ, make sure your parentheses are right, and you can stop here. Because there's a decent chance you're going to make a mistake as you do some of that arithmetic. And on FRQ, you can stop up here. But we want to practice like it's multiple choice because we'll see these on multiple choice a lot. Okay, questions? All right, your assignment is going to be 290. I don't think that's right. Because some of those are the ones you had last night. I think that's old. Let's see. Yeah, that's not right. Alright, you're going to same page as last night. 342. And you guys are going to do let's do 71 through 81 odd. I think that'll give you adequate practice there. Is there a reason I didn't give 81? I don't think I did. Let me tell you that on 81, u is going to equal 3 over x. That one might be a little tricky. I think you should be okay on the others.